Alright, in this video we're going to talk about the theories of polynomial functions. And there's two sections of discussions of polynomial functions. So we're going to start with a couple of theories in this video, and then we'll have a follow-up with some others. Okay, I like to think of what we're talking about in this video. Each of these theories or theorems are really geared towards helping us find the zeros of a polynomial. And there's a lot of ways that we can do that, and there's a lot of hints that we can get, and sometimes we can work those hints together to help us really get some information about the polynomial. So one of the tools that we're going to use to help us look at these theories is division. So we want to be able to take a polynomial and divide it. So there's something called a division algorithm, and this really applies to all division. We're going to apply it to dividing polynomials, but you could take a polynomial, I guess that part is usually called the dividend, and then you can divide it by something. Maybe you're going to divide it by x minus 5. Some other smaller polynomial, that's called the divisor. When you divide, the result that you get is called the quotient. If it doesn't go in evenly, there's a remainder. And so we could write our result as the quotient plus the remainder divided by the divisor. So we have the remainder over the divisor because anything left over did not get divided yet, and so it's still written as a fraction. Okay, so we can use this division algorithm when we divide with long division, which is what we're going to do first, and with what's called synthetic division. So I want to show you both of those today, and then we'll add some theorems to that. Let's start with polynomial division. It's a lot like long division when you learn in 3rd or 4th grade. It's just that instead of digits, we have terms, and the terms are organized from highest power on the variable down to lowest. Okay, so if we did some dividing here, we put in our division symbol. If there are any terms missing, we want to account for those. So I'm learning some of these words. The dividend, okay, is what goes inside. And our dividend for this particular example does not have any missing powers of x. It counts right down, so we don't have to fill in the gaps. But the divisor is missing x to the first power in the middle here. So we're going to write it as 2x squared plus 0x minus 3. That 0 is just holding the place of the x to the first term, just like a 0 would hold the place for like the 10th digit or the hundreds, okay? And then we're going to divide just like we would. We're going to use the front of each polynomial to divide. So we would want to think, okay, 2x squared multiplied by what will give me 4x cubed. I'm sorry, 8x cubed. I was thinking ahead. 4x would get us from 2x squared to 8x cubed. And maybe it's better to line it up with its power of x, I guess. Okay, so then 4x multiplied by what we have out here would give us 8x cubed. 4x times 0x would give us 0x squared. 4x times negative 3 would give us a minus 12x. And then we're going to subtract, just like we would in normal division. I always like to put the minus out here with parentheses because remember that negative's technically going to be distributed. You could go through and change all the signs if you like. 8x cubed minus 8x cubed will be 0. We set it up that way. 10x squared minus 0x squared will be 10x squared. Negative 12x minus negative 12x will be like negative 12x plus 12x, which will be 0x. And then we're going to bring down the next term, just like we would bring down the next digit with the standard multiplication. Then we do that whole process again. 2x squared multiplied by what is going to give us 10x squared? That would be a 5. So now we're going to multiply 5 times everything out here, times the divisor. 5 times 2x squared would be 10x squared. 5 times 0x would be 0x. And 5 times negative 3 would be negative 15. This one comes out pretty nicely. They won't always be this nice and even, but we'll take it. 10x squared minus 10x squared is 0. 0x minus 0x is 0. Negative 15 minus negative 15 is like negative 15 plus 15 is going to give us 0. And we're done. So our quotient would be 4x plus 5. Our remainder would be 0. Okay, so if you wanted to write it using the division algorithm, let's see, we'll write it like this. 8x cubed plus 10x squared minus 12x minus 15 divided by 2x squared minus 3 equals 4x plus 5. If we had a remainder, let's say we subtracted here and got 5, we would add 5 over 2x squared minus 3. This time we don't. In the case where we don't have a remainder, this means that 2x squared minus 3 divides in evenly, which means it's a factor of this big polynomial on top. If I were to factor 8x cubed plus 10x squared minus 12x minus 15, I would get 2x squared minus 3 and 4x plus 5. Okay, in this chapter, we're going to use the division because we are going to be dealing with polynomials that are too big for our current factoring tools to help us. So we won't be able to factor them. This one I think we could have factored by grouping and gotten to this result. But there are many in this chapter where that's not the case. We may have 4 terms and grouping doesn't work, or we may have more than 4 terms and we don't really have a strategy for that. So that's why we're going to rely on the division. Okay, and we are going to talk about factors in this video, so I'm going to go ahead and add this in right here. And we'll maybe add some information around it, but 2x squared minus 3 is a factor. We're going to be identifying that throughout the video today. Okay, so let's look at the next. So that's polynomial long division. You might be excited to know that there's a shortcut that you can use. All right. There is a use for long division. This shortcut doesn't always work. It only works in a special scenario, but it is nice. So we'll definitely look at it. Synthetic division is a shortcut method of performing long division, and we can use it when we're dividing by a linear factor. Linear would mean that x is to the first power. So it can be x minus a number or x plus a number. So to give you an example, we're going to divide this polynomial here by x minus 4. This is a good example because if you tried to factor this polynomial, it's 4 terms, so you might try to use grouping, but grouping is not going to work. And so this is the main motivation for us to look at polynomial division and synthetic division. Okay, so synthetic division is a little bit different. It is a shortcut. instead of putting the whole polynomial underneath the division symbol, we are only going to keep track of the coefficients in order. So I'm not going to write the x cubed. I'm going to write the 1. You know, there's an implied 1 here in front of the x cubed. I'm not going to write the x squared. I'm just going to write the -2 that's out front. I guess it is a requirement that you have your terms in order. And just like before, if there were any missing powers of x, we would put a 0 in the place of that missing power. Okay, on the outside, we're going to use the opposite of what we see here. We see a -4. We're going to be dividing by 4. There are a lot of reasons for that. You can think of this as the factor and this is the 0. So if you set this equal to 0, that's the number you're dividing by. That's related. Okay, and then the process, instead of doing that subtraction like we did in long division, we're going to be doing addition. And so the reversing of this sign allows us to do that. Okay, now we're dividing x cubed, 1x cubed divided by 1x. We're always going to be dividing by 1x for this method. So whatever the first number is, we're going to bring it down. Because when we divide by x, we don't really change the coefficient in front. Then we're going to multiply by 4, just like we multiplied in the long division. So 4 times 1 gives me 4. And then remember we said because we've changed the sign, we're not going to subtract, we're going to add. -2 plus 4 gives me 2. And I'm going to continue that process. 4 times 2 gives me 8. 11. Oops, I'm sorry. That should be a -11. I missed that. I was about to get worried because we were about to get a big number. -11, that's better, plus 8, -3. And then 4 times -3 gives me -12. And 12 plus -12 gives me 0. Okay, so in this method, the quotient is down here at the bottom. And the numbers here are the coefficients of the quotient. And the degree has gone down by 1. So x cubed divided by x to the first would give me x squared. So this 1 will be the coefficient for x squared. 2 will be the coefficient for x. 3 will be the constant, the just plain number part. And the last number will be the remainder. So sometimes we draw a line there. You don't have to do that. This is the remainder. Okay, so if we wanted to write out the solution, I'll just do it the same as we did last example. We're taking this polynomial divided by x minus 4, and the result that we get is 1x squared, I'm just going to write it as x squared, plus 2x minus 3. And just like before, we can use this because we have 0 remainder. This divides in evenly. If we had a remainder, we would add it over here, whatever we got as the remainder, over x minus 4. It didn't happen in this example. We'll do one like that in a second. If it goes in evenly, we can use that to help us factor our polynomial. So this polynomial is the same as x minus 4 times x squared plus 2x minus 3. Now, that's all this question asks us to do. Sometimes when we do the division and we find a factor, that gets us started with the factoring process, and then we could continue from here. So if we wanted to, we could sit down and factor what's left, and that way we would be able to factor the entire polynomial. Okay, let's try another example. I'll do that for now. This actually is coming from your book in this section. It's number 29. So we're going to divide this polynomial by x plus 1. If you want to, you can think of this as x minus negative 1. And this is the number that's going to be going on the outside. Okay, or you could set the factor equal to 0, and that would give you the number that's going to be on the outside. Now we're going to notice that there's a missing x squared term right here. So when we list the coefficients, we have -2. We're going to put in a 0 to hold the place for x squared. This minus here is a -1, and then -2. Okay, we're going to bring down the first number. Remember, the reason is because we're dividing by just x, and that's not going to change the coefficient at all. Then we're going to multiply. -1 times -2 is 2. Then we're going to add 0 plus 2. Multiply, -1 times 2, and then add. Multiply, and then add. Okay, and just like before, the degree of the quotient, these are the coefficients for the quotient, the degree is going to go down by 1. So our original polynomial was x cubed, but we're dividing by something that's x to the first, so our solution is going to be starting with x squared, -2x squared. And again, this is the remainder. Okay, so if we want to write that out, we took this polynomial and divided it by x plus 1, and this is what we got, -2x squared plus 2x minus 3. This is the first time so far that we've had a remainder. So we're going to add the remainder over the divisor, which is because the 1 did not get divided. And so it stays over x plus 1. Okay, this one did not divide in evenly, so we cannot write it in that factored format. I guess you could write it like this. So it would be factorable, except we had that 1 left over. So if we multiply these two things, we almost get there, and then we have to add the remainder. That's another way you can represent this. Because of the remainder, x plus 1 is not a factor. And like I said, we're going to spell that out in just a second with one of the theorems. Okay, I hope that gave you a good explanation of synthetic division. It's going to take some practice, so the book has lots of practice problems you can use. Really, you could just divide any two polynomials and give yourself some good practice. Then we can look at some of these theorems. Okay, so the first one we have here is called the remainder theorem. It says if the polynomial, and I used f of x instead of p of x, is divided by x minus k, then the remainder is equal to f of k. So when I divide by x minus k, whatever I get left over, that's the function evaluated at the number k. And you might be like, whoa, I don't know, for me this was kind of mind-blowing. It was hard for me to wrap my head around how that could be true. Let me put up here the work we just did. I thought we could use that as an example. So we just divided, fit all this on the screen, okay, this polynomial, so this is the same number 29, we just divided it by x plus 1, and we got 1 as the remainder. So let's take k. K is the number we used outside of our synthetic division. And let's plug that into the function and see if this remainder theorem is indeed true. Okay, so if I plug in -1, whoops, I have -2 times -1 cubed minus -1 minus 2. So that's going to give me -2 times -1, because if I cube -1, I'm still going to get -1, plus 1 minus 2. So really this is 2, plus 1 is 3, minus 2 would be 1. And it works. We got a remainder of 1, and if we plugged in k, the value we got was 1. So if your function was really complicated and you didn't want to plug it in, you could use the synthetic division to find the value. Sometimes that's helpful, sometimes it's not. I think that's a little bit of preference there, but it's a tool you could use. So let's try it out on one more time. This is number 42 from your book. Here's the polynomial, x to the 4th plus 2x squared minus 10. K is the square root of 3. And we're going to use the synthetic division to find the value of p when we plug in x to be the square root of 3. Okay, so let's do the synthetic division. We're going to do the square root of 3 out here. Notice we have some missing powers of x. We're missing x cubed, and we're missing x to the first. So we have 1x to the 4th, 0x cubed, 2x squared, 0x minus 10. We're going to bring down the 1, multiply by square root of 3, and then add down 0 plus square root of 3, and repeat. Multiply square root of 3 times the square root of 3 is 3. Add down, it's 5. Multiply square root of 3 times 5 is 5 square root of 3. Add down, and then multiply square root of 3 times 5 square root of 3. That's like 5 times 3, because the two square roots multiply to be 3. So that's 15. And add down is 5. So 5 is my remainder. All right, so if you don't believe that this remainder theorem works, you could check yourself. Okay, so let's do that. So let's just see if this is true. If I plug in the square root of 3, let's do that and see if I get 5. Okay, the square root of 3 raised to the 4th power is like 3 times 3. You think about that? So, or 3 squared, so that's 9. This is going to be like 2 times 3, so that's 6, minus 10. So this is 15 minus 10, which is 5. And it works. Okay, so now you know that plugging the number into the function is the same as doing synthetic division, dividing by that factor. That's called the remainder theorem. The next theorem that we'll look at is called the factor theorem. Some of these overlap a little bit, so some of this information you'll be like, we already said this, but this is the theorem. The factor theorem says a polynomial function p of x has a factor x minus k if and only if p of k equals 0. You'll remember that p of k is the same as the remainder. That's the theorem we just looked at. So if the remainder is 0, then it divides in evenly, and it is a factor. Okay, if you can connect all those things in your mind. In number 42, we just did that one. We plugged in the square root of 3, we got 5. So that's the remainder. The remainder is not 0, so x minus 3 square root of 3 is not a factor. We did plenty others in this video already that were factors, and we pointed out that the remainder was 0. A factor is going to be divided evenly if that value is called a 0. It means that we plug it in, it makes the function 0. Okay. Then we have another fact here, zeros and factors. If x, okay, we just said this. If x minus k is a factor, then k is a 0 of the function. There can be real zeros and complex zeros. Real zeros show up on the graph, and we've sort of talked about that in the last week or so. Okay, so let's try one more. This is number 79. It says, is k a 0 of p of x? If so, factor p of x into linear factors. So to test to see if it's a 0, we can do the synthetic division. What will we know from this synthetic division that tells us it's a 0? We will know it's a 0 if, when we divide, we get remainder to be 0. That means it's a factor. We have found a factor, and the value for k is a 0. I know there's a lot of words, but... Okay, so let's do the synthetic division. We'll put the -1 out front. We don't have any missing powers of x this time, so we don't need any zeros. So here's our coefficients. Maybe at this point you're a pro now on synthetic division, now that we've done several. We're going to bring down the first number, multiply by -1, and add down. Then multiply again by -1, and add down. Multiply by -1, and add down. Okay, this is our remainder. So is k a 0 of p of x? We would say yes. -1 is a 0. Okay. Then we can go a little bit further. Okay. So if we use -1 here, what is the factor? The factor would be x minus -1 or x plus 1. Okay, so x plus 1 is a factor. All right, so that means when I take this polynomial and I divide it by x plus 1, which is what I just did, I get this result. So I could take my polynomial, all this stuff right here, that must be equal to x plus 1 times my quotient. Remember this, these are the coefficients, and remember the degree of the polynomial. When I move to the quotient, I go down by 1 exponent. So this starts with x squared minus 3x minus 4. Remember, I didn't have a remainder, so I don't have to add anything there. And now it is a 0, and so it's asking us to factor this into linear factors. This factor is linear because it has x to the first. This factor is not, so we would like to continue factoring all the way. We need two numbers that multiply to be 4. I'm thinking 4 and 1 are going to work here. And we want these two numbers in the back to add to be -3. So I want a -4 and a +1. 4 and 1 + 3 = 6. 6 + 1 = 9. 9 + 4 = 22. 22 + 1 = 24. 24 + 1 = 26. 26 + 1 = 28. 28 + 1 = 30. 30 + 1 = 40. 40 + 1 = 50. 50 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 = 55. 55 + 1 we were able to factor it completely. And this is how we're going to be using the synthetic division. We're going to come up with some numbers to try. We're going to use the synthetic division since it's quick. And any number that gives us a 0 remainder, we're going to know that that's producing a factor. And that's going to help us break the polynomial down. Okay, the last theorem is called the intermediate value theorem. So let's read that. It says if p of x is a polynomial function with real coefficients, that means that the numbers in front of the powers of x are real numbers. And if p of a and p of b are opposite in sign, then there exists at least one real 0 between x equals a and x equals b. Okay, so let's try to make some sense out of that. We just took and factored a polynomial, right, all the way. Here's what we got. Let's sketch the graph of this polynomial real quick. So the zeros, I'll just jot some things down off to the side, are -1 and 4 if we set each of these factors equal to 0. And the end behavior, if we were to go back to the multiplied out version, x cubed was in the front. So that means the ends are going to go in opposite direction. The number out front here is positive, so when x gets really big, it's going to go up. And when x gets really negative, it's going to go down. The multiplicity, we see that the -1 has a multiplicity of 2, which is even. So it's going to bounce back onto the same side. Somewhere in here there's a turning point. We're going to estimate that part. And then it's going to come and cross over at x equals 4. All right, maybe this is going backwards a little because now we have the shape of the graph. And we know what the zeros are, but let's just plug some numbers in so you can see how this works. So this is saying that if I pick two numbers and I plug them into my function, or I use the synthetic division to calculate the value, if those two numbers give me y values that are opposite in sign, then somewhere in between there must be a 0. So if I plug in 3 to my function up here, 3 plus 1 would be 4 squared, times 3 minus 4 would be -1. So that's going to give me -16. If I plug in 5 into my polynomial here, 5 plus 1 is going to give me 6 squared. 5 minus 4 is 1. So that's going to give me 36. Whoops, 36. And it's positive. Okay, so notice I'm changing sign. I'm going from below the x-axis to above the x-axis. And in order for that to happen, I must have crossed the x-axis somewhere in the middle. So this theorem says, hey, there is a 0 between x equals 3 and x equals 5. Remember we said that these theorems are like tools to help us find the zeros of a function and investigate the function further. We know there's a 0 at 4. We're like, okay, yeah, I understand that. But if we didn't know that, we could test, and if this happened, that would give us some more information to help us out. Let's look one more example before we finish. Same kind of question. This is number 9 from your book. So here's another polynomial, and the question is there a 0 between 1 and 2? So we could plug in 1. We plug in 1, we're going to have 3 minus 2, so that would be 1 minus 6, so negative 5. If we plug in 2, we'll have 4 times 3, so that's 12. 12 minus 4, that's 8. Minus 6 is positive 2. They're opposite in sign, so the answer would be yes. There is a 0 between 1 and 2. Okay, now I plugged this into the function. You could also use 1 and do synthetic division and look at the remainder. Remember we said the remainder is going to be the same as the value of the function there. So if you thought that would be easier to do the synthetic division, you could definitely do that. All right, I hope this gave you a little bit of a picture of these theorems. We'll definitely have some time to practice them in class. The next video is going to give us a couple more theorems, and then we're going to really start working on putting all these together to help us find the zeros of a bigger polynomial function of higher degree. Good luck. See you next time.